Hello everyone, Mr. Schultz here. Welcome to Integrated 2, 1-1. Perpendicular bisectors of statements. Make sure you write your title and your information in the top left-hand right corners. So before we begin, let's talk about a theorem. A theorem is a statement that can be proven true using undefined terms, definitions, and postulates. I can make these statements, like for example, our hypothesis is like if I am thirsty, then I will drink water. We're also going to be talking about converse to theorems. Converse to theorems are statements that are formed by exchanging the hypothesis and the conclusion of a conditional statement. Well, let's talk about that. So once again, if I am thirsty, I could say, so if I am thirsty, then I will drink water. So another way of saying this is if A, then B. Well, the converse theorem would be if B, then A. We just switch it around. If I drink water, then I am thirsty. We might go into conditional tables later, but that's on our motions right now. We're going to be talking about perpendicular bisector theorems and stuff like that using our constructions that we've done previously. Let's go on. So let's talk about the perpendicular bisector theorem. So if a point is on a perpendicular bisector, so let's write that in, perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay, well, what does that mean? Well, that means any point along this line right here is going to be equal in distance. So let's add this like E right here. Now, hypothetically, we should have used a ruler on that, but if we did like A to E and B to E, then those would be equidistant, also known as equal in measure. So if CD is perpendicular, it is a bisector of AB, meaning it cuts it in half. Then any point along this line will be equal to A and to B. You could tell that when we were drawing circles, because the definition of a circle, that was weird, is everything along the edge of the circle is equidistant from the center. Okay, let's go on. So the converse of this perpendicular bisector theorem is the following. If a point is equidistant from the endpoints of a segment, then it is equidistant from the endpoints. Oh, now there's an error. This should not be this one. This is, I didn't switch. So I'm going to quickly type it in. Give me a second. There we go. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So, for example, if we had a line right here, and it is equidistant from 2 points right here, let's call it A and B, then it is on the perpendicular bisector. It's pretty much saying, hey, if these are equal, then this is the perpendicular bisector. previously it was like, hey, if this is on the perpendicular bisector, then the points are equal. All right, let's continue. So let's use our example. Use the perpendicular bisector theorem to find EF. All right, so we know that EF is equal to HF. So EF equals HF. How do we know this? Because this is the perpendicular bisector of EH. Because of the perpendicular, so the perpendicular bisector states this. Bisector theorem. Next up. So we know that we can substitute the values. EF is 4a minus 15. So we can write 4a minus 15 is equal to a plus 12. And this is, what is it called when we switch it out? Well, when we switch it out, it's called substitution. All right, next up. Now we just need to solve. You know, we could subtract by a on both sides. And we get 3a minus 15 is equal to 12. Now we can add 15 on both sides. We get 27 is equal to 3a. And then we can divide by 3a on both sides, or divide by 3 on both sides. We get a is equal to 9. So if we were to go through each one of these, we could literally say, hey, this is the subtraction property of equality. And then when we added 15, we did the addition property of equality. And then when we divided, what did we do? We used the division property of equality. And then we just simplified, simplified if we wanted to say that. So we solve for A, but it's asking, hey, what is EF? EF is going to be 4a minus 15. We know that a is 9, so we could do a substitution to substitute 9 for a right there. When we do that, we get 36 minus 15. And if we subtract it out, we can see that EF is 21 units. So there's a brief look on solving using proofs. All right, let's go on. Example 2, use the converse of the perpendicular theorem. All right, let's hold up. Okay, so the first thing we see is WZ is equal to WX. The next thing we see is, forgot to put it, is perpendicular. WY is perpendicular to line XZ. So they're perpendicular. So knowing that, we can use the converse, get that out of there. We can use the converse to the perpendicular bisector right now. So we understand that WY is the perpendicular bisector of XZ because we understand that, hey, look, these two are equivalent, and hey, look, this is perpendicular. So therefore, WY has to be the perpendicular bisector of XZ. So using that logic, we can say, hey, we understand that by the definition of segment bisector, because we understand that, hey, WY is a segment bisector, it's bisecting XZ, we understand that ZY is equal to XY. And because ZY is equal to 22.4 units, then xy has to equal 22.4 units. All right, let's go on. So just like when we were drawing either our circumcenter or our in-center circles, we had three concurrent lines. The three concurrent lines are, when three or more lines intersect at a common point. Like if we look right here, we look at this triangle right here, we see that, hey look, there's at least three lines that meet at D right here. At this point, the point is called, the point of intersection of concurrent lines is called the point of concurrence. Now, circumcenter. If we do perpendicular bisectors, so perpendicular bisectors. So basically, if we draw the perpendicular bisectors of each of the sides, we would get the circumcenter, or a circle that goes around the triangle, not in it, around it. All right, let's talk about the circumcenter theorem. The perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle, meaning each of the 3 points of the triangle are equidistant. Let's show you. All right, that took me way too long, but this is what the circumcenter is. Each of these points is equal in distance from the center, the circumcenter. So we have to use the circumcenter theorem to find BF if D is the circumcenter of triangle ABC. So we know that AC is 9. All right, so from A to C is 9. Okay, cool. We know DE is 1.83. We know that DF is 1.53. So let's break this down for you. You have to kind of think beyond and think, all right, what can I use to help me out? I know that AC is equal to 9, and I know that E is the perpendicular bisector. So that means EC right here has to be 4.5. And now we're getting into the tricky part. Now, hopefully you watched one of the 6-point intro pre-6.1 videos where we talked about the Pythagorean Theorem, because we're going to have to go over it right now. Now, DC, so I know that a squared in the Pythagorean Theorem, a squared plus b squared is equal to c squared. Well, that means the leg of one of the right angle triangle, 1.83 squared plus b squared, 4.5 squared, is equal to c squared, or dc. Whatever dc is, squared. So if I actually solve this, I get like 3.35 plus 20.25 is equal to dc, still squared. All right, well now, if I actually get it, I'm going to get 23.6, and then I'm going to find the square root of that to cancel out the squaring right here. So I'd get dc is equal to plus or minus 4.86, because it could be both positive or negative. But wait, can we have negative distances? Can you eat negative pieces of fruit? No. So it's just going to be positive 4.86. So now I know that this guy is equal to 4.86. All right, so remember the perpendicular bisector theorem? Or actually, no, not the perpendicular bisector. This is going to be the circumcenter theorem. So the distance from D to the vertex is equal to each other. So D to the vertex is equal. So if this is 4.6, is DC is 4.6, then BD has to be 4.86 as well. Well, if that's the case, hey look, this is another example of a right triangle. So I know this is the hypotenuse. So I would have 4.86 squared is equal to 1.53, a leg of it, squared, plus BF squared. Now, solving it, I would get 23.62 is equal to 2.34 plus BF squared. And this would just lead into like subtracting by 2.34 on both sides, solving for BF squared. But if I solve for it, I get 21.28 is BF squared. But I don't want to solve for the square of it. I want to solve for just it. So I'm going to do the square root, and I would get plus or minus 4.61 is equal to BF. So this is a lot of work just to figure out the problem. So let's talk about it. Why is this important? There's no clear-cut way to do it. Yes, there's really like one way you're supposed to solve it, and it's kind of set up for you to do it, but you have to like do some mental gymnastics and go, okay, wait, what do I know to make this possible? And think, all right, if I know this, then I know that. If I know that, then I will be able to do this. And that's what geometry is about. It's all about logic and finding the solution. All right, let's go on. Example 4, use perpendicular bisectors. All right, so this one's a little bit easier in the fact they give us most of the problem. So looking at this, Alonzo wants to install a fountain in his triangular garden. Where should Alonzo place the fountain so it is equidistant from the vertices of the garden? Now, using, or actually understanding the circumcenter, that's where, hey look, the three lines that are perpendicular to the sides of a triangle is the circumcenter. At this point right here, at this point where I'm circling, that's equal in distance from each of the vertices. Well, and if that's the case, then that's where we should build our fountain. All right, well, where is it? Alonzo should build his fountain at the circumcenter, which is, it looks like it's at 0, comma, maybe 3.8. It's just a little under 4. All right, that's it. We have to understand, what does this point represent for, like, what does it mean to be the circumcenter? All right, let's go on.